and we're specifically going to look at Hess's law and the law of conservation of energy. So we're going to explore Hess's law and the law of conservation of energy, and we're going to do some examples. Hess's law is specifically important for exam questions. So we'll start with the law of conservation of energy, and this is just simply a definition. And the law of conservation of energy states that energy cannot be created or destroyed, only changed from one form to another. And you should remember that from junior cert. So a Russian chemist called Hess modified this law in terms of heat changes to come up with his own law called Hess's law. Hess's law states that the heat change for a given reaction is the same whether it takes place in one step or in a series of steps. So let's look at a real simple example to see what this means. So if we take a look at this little example here, we can see that we start off with carbon, and there's two possible directions that it can go. So if we look at the right hand direction first, where we add 1 mole of oxygen gas, we see that we produce carbon dioxide. So this is way 1 to get to our product. So that's it been done in a single step. However, it can also be done in 2 steps. So we can start with our carbon and add half a mole of oxygen to give carbon monoxide, and this would be, we'll call it 2. And then once we form the carbon monoxide, we can add another half mole of oxygen to produce carbon dioxide. So we'll call that 3. So that means that there is 3 reactions here. The first reaction is the single step of going from carbon and oxygen to produce carbon dioxide. And step 2 and 3 involve going from carbon, adding half an oxygen to give carbon monoxide, and carbon monoxide adding half of oxygen to give carbon dioxide. So you can see here that we have a delta H value missing for step 2. Now, Hess's law states that if a chemical reaction takes place in a number of stages, the sum of the heat changes in the separate stages is equal to the heat change if the reaction was carried out in one stage. So that must mean that step 2 and step 3 added together must equal the heat change in step 1. So here we must say that the heat change of equation 1 must equal the heat change of equation 2 plus equation 3. So if we fill in everything we know that the heat change for equation 1 is minus 394. We're trying to figure out what the heat change for equation 2 is, and we know that the heat change for equation 3 is minus 283. So what we can do is we can bring this 283 across to get to, or the question mark, on its own. And once we solve that, we figure out that question mark equals minus 111 kilojoules per mole. So that means that this heat here is actually minus 111 kilojoules per mole. Now, to check that your answer is correct, you should add together 2 and 3 and see if it equals 1. So 2 is minus 111, 3 is minus 283, and if you put that into your calculator and add it together, that does give you minus 394. So you know that your answer is correct. Now this is a very simplistic example for Hess's law, so let's look at more complicated examples now. So we use Hess's law to often calculate the heat of formation of a compound using the heat of formation of other compounds and heats of reactions. So when using Hess's law, we have to take the following steps. You write down the equations that you require, and these are usually common sense equations that you would be easily able to understand or construct in your head. And then using the equations given in the question, or the ones that you create, you get each part of the equation you require by multiplying and reversing. So that sounds a little bit complicated, but it's actually not, so we'll just do an example to explain. So here's an example. Calculate the heat of formation of methane from the following data. So it gives you that the heat of formation of carbon dioxide is minus 393, that the heat of formation of water is minus 286, and that the combustion of methane is minus 897. So the first step is to write out the equation that we want. So we want the heat of formation of methane. So we know that we're going to form 1 mole of methane. So on the right hand side of our balanced equation we want CH4. We know that methane is made up of carbon and hydrogen. So carbon exists as C and hydrogen exists as H2. So to balance that equation we must have 2 hydrogens. So this is now our equation that we're working towards at the end. So with all the work we do in this equation, in this question, what we want to end up with this equation here at the end. So the first step that I would probably do is I would label each of the equations that's given to us in the question. So 1, 2 and 3. So let's look at equation 1 first. Equation 1 is carbon plus oxygen giving us carbon dioxide. So if I look here, the thing that is of interest to me in this equation is the carbon. And I can see that the carbon is on the left-hand side in this equation and it is on the left-hand side in the equation we want at the end. So I am going to suggest that for equation 1 we just leave it alone. Next, let's look at equation 2. And equation 2 has hydrogen plus half of oxygen giving us H2O. Now, if we look, the molecule that's of interest in this equation is the H2, and we can see that we've H2 in this equation, but in the equation that we're working towards at the end we have 2H2. So what we want to do with this equation here is we want to double it. We want to multiply it by 2. So that will leave us with 2H2 plus O2 forms 2H2O, and if you double all of the equation you also must double the delta H, so we get delta H equals minus 572. The last one then is we're going to look at equation 3, and we see equation 3 is CH4 plus 2O2 goes to C. Last one then is we're going to look at equation 3, and we see equation 3 is CH4 plus 2O2 goes to CO2 plus 2H2O, and we see that delta H there is minus 879. So for this equation, the molecule of interest is our methane, which is CH4, and we can see that it's on the left hand side in this equation, but we want it to be on the right. So what we must do is we must reverse equation 3, or it may be referred to as flipping equation 3. So equation 3 will become CO2 plus 2H2O goes to CH4 plus 2O2. Now, if you flip or reverse an equation, you must change the sign of your delta H. That's the key thing. So, at this point, we are dealing now with the equations that I am highlighting here in blue. These are the equations that we are going to use now to get our final equation. So what I'm going to do now is I'm going to write down all of the reactants and all of the products together. So the reactants, let's write them. It's carbon plus oxygen plus 2 hydrogen plus oxygen plus carbon dioxide plus water. They are all of your reactants. And then all of your products are carbon dioxide, water, methane, and oxygen. And we also must write down the delta H. So the delta H we have, if you can see, we've added all of our equations together in theory. So you must add together all of your delta H's. So you're going to do minus 393 plus minus 572 plus 879. And what you get is you get delta H is equal to minus 86 kilojoules per mole. So now, if we look at the equations, we can start cancelling out things that are the same on both sides. So if I look, I can see that I have one carbon dioxide on the right-hand side and one carbon dioxide on the left. So they can cancel out. Something else that can cancel out is our waters. I have 2H2O on the reactant side and 2H2O on the product side. Then if I look on the product side, I can see I have two oxygens. And if I look on the reactant side, I can see I have oxygen and oxygen. So these two oxygens can cancel out with these two oxygens here. And what you will be left with at the end is you will be left with C plus 2H2 goes to CH4, and you get that your heat of formation is minus 86 kilojoules per mole. And that's your question complete. So let's try another example. This one's a little bit more complicated as the equations aren't given to you. It says the combustion of liquid benzene is described by the following equation. Given the heats of formation of carbon dioxide gas, liquid water and liquid benzene are minus 394, minus 286 and 39 kilojoules respectively, calculate the heat of combustion of liquid benzene. So the reaction for the heat of combustion is here. It's given to you already. What you have to form here is you need to form your reactions showing the heat of formation of carbon dioxide, liquid water and liquid benzene, and you're going to use those to try and form this equation here for the combustion of liquid benzene. So let's give that a go. So the equation that we want to end up with at the end is 2C6H6 plus 15O2 goes to 12CO2 plus 6H2O, and we're looking to try and find the delta H of that. But that's what we want to end up with at the end, so I'm going to highlight that in blue for us. Now what I'm going to do is we need to write out our three equations for our heats of formation. So just to remind you, the definition for heat of formation is the heat change that takes place when 1 mole of a compound in its standard state is formed from the elements in its standard state. So if we're trying to produce carbon dioxide, we know that we're going to have carbon dioxide on our product side, and it's made up of carbon, which exists as C, and oxygen, which exists as O2. And the delta H there is minus 394. So that equation is perfectly fine. That is, we're going to label that equation 1. The next equation that we want to look at is the heat formation of water, and water is H2O. So it's composed of hydrogen and oxygen, but we need half O2 in order for the equation to be balanced, and delta H there is minus 286. So we're going to call that equation number 2. The last equation is the formation of liquid benzene. So benzene is formed by C6H6. So we're going to need carbon and hydrogen, but we're going to need 6 carbons and 3 of the hydrogens because they're H2, and delta H there is equal to 39. And that is equation 3. So at this point now, we're ready to go. So let's start with equation 1. Equation 1 has carbon plus oxygen, giving us CO2, and delta H equals minus 394. So here we see that what is of interest to us is our oxygen and our carbon dioxide. But if we look at our we can see that we have two molecules of interest here. We have oxygen and carbon dioxide. Now, looking at the other equations, this here is the only equation that has carbon dioxide present in it. So we're going to focus on the carbon dioxide. And we can see that we've one carbon dioxide on our product side, but in our reaction we actually want to have 12. So what I need to do with this equation is I need to multiply it by 12. So that will give me 12 carbons plus 12 oxygens gives me 12 CO2, and my delta H there is going to be minus 394 by 12, which is minus 4,728. So that's that equation dealt with for the minute. If we move on to equation 2, we can see that we have H2 plus a half O2, and that goes to H2O with a delta H of minus 286. So if we look here, again of interest to us is the half O2 and the water, but this is the only equation that has H2O in it. So we're going to specifically look at the H2O. So we can see here we've one H2O on our product side, but we need to have 6 H2Os. So what we do is we multiply this equation by O, and you multiply your delta H, which is minus 286, you multiply the minus 286 by 6, and you get minus 1,716. So I'm just going to highlight those two equations now that we're currently going to be working with. So these are the new equations that we're going to be working with. The last equation we want to look at then is the third equation, which is equation 3, and it is 6C plus 3H2 goes to form C6H6, and delta H is equal to 39. Now, we can see here that the main point of interest for us here is our C6H6. It's on the product side here, and it's on the reactant side in our equation that we want. So the first thing I would say to do is I would reverse or flip. So that means that this equation will become C6H6 going to 6C plus 3H2, and delta H now becomes minus 39. But if we look now, we're still not fully there because we've got the benzene on the correct side now. The C6H6 is on the reactant side. We only have one of it here, but we need 2. So we now need to multiply this by 2, and that gives us 2C6H6 goes to 12C plus 6H2, and our delta H becomes minus 39 by 2, which is minus 78. So that is now our equation, our final equation of interest. So if we look, just to compare, I can see that I have the 2C6H6 and the 2C6H6. Do I have my 15O2? I actually do, because I've got 12 of them in this equation and 3 of them here. So when I add those together, that will give me 15. Have I got my 12CO2? I do, my 12CO2. Have I got my 6H2O? I do, I have my 6H2O. So let's go and add everything together now and see what happens. So if I write this out, I have 12C plus 12O2 plus 6H2 plus 3O2 plus 2C6H6, and that goes to 12CO2 plus 6H2O plus 12C plus 6H2. And delta H is gotten by adding all of the heats of reaction together. So you do minus 4728 plus minus 1716 plus minus 78. and that gives you minus 6,522. Now, as per the last example, let's try and cancel some things out. So the first thing I can see is I have 12C on the left and I have 12C on the right, so they can go. I have 6H2 on the left and 6H2 on the right, so they can go. And that's kind of it. So if we look now and rewrite our equation fully, we can see that we have 2C6H6 plus the 12 and the 3 can add together to give you 15O2, and that goes to 12CO2 plus 6H2O, and delta H is equal to minus 6,522 kilojoules per mole. Now, the only thing we want here is the heat of combustion. If you go back to your example or your definition on heat of combustion of a substance is the heat change when 1 mole of a substance is burned in excess oxygen. Here, this equation is for 2 moles. So the heat of combustion of 1 mole of our benzene is actually half of the 6,522. So we actually say that delta H of C6H6 is equal to the minus 6,522 divided by 2, which is minus 3,261 kilojoules per mole. And at that point, this question is now complete. Problems based around Hess's law can also be solved using a formula where the heat of reaction equals the sum of the heats of formation of the products minus the sum of the heats of formations of the reactants of the reaction. This can be used, however, I do recommend that you do it out the long way with. So let's look at the same example we've done in the previous slides and do it with the idea of the formula in mind. So here's our formula at the top. The heat of reaction is equal to the sum of the heat formations of the products minus the sum of the heat formations of the reactants. So I would say for our products to start with, our products we have 12CO2, so that will be 12 times the heat of formation of carbon dioxide, which is minus 394, and that gives you minus 4,728, and then we have 6H2O, and that is 6 times minus 286, so that equals minus 1,716. Now if we look at our reactants, we can see that we have benzene, which is 2C6H6, so that is 2 by 39, which is 78. And then we have 15O2. Now that's 15 by 0 because oxygen, it's just a molecule by itself, so it will always have a value of 0. Same with hydrogen, if it was by itself, H2 would have a value of 0, so that gives me 0. So now I can see that delta HR is equal to minus 4,728 plus minus 1,716, and you take away from that 78 plus 0. And if you, let's break this down I suppose into steps. The first bracket is minus 6,444, and you take away from that 78, and what you get is minus 6,522 kilojoules, but that is for 2 moles of our benzene. So what we need to do is we need to divide that answer by 2, and what you will get is you will get minus 3,261 kilojoules per mole, as we did when we done the equations method. I recommend that you follow the equations method, but if you prefer the formula, feel free to use it. So that's it for this video. Have a read over the learning intentions to make sure you understand everything we've gone through.